tells you the proportion that's less than or equal to that value in our distribution. There is a command in your calculator that will show you the same thing for a binomial situation, less than or equal to. It's binomial CDF. So if you go back into your calculator and you type in binomial CDF of, and then you talk about what these different things are. So I have 5 different things that could occur, and I know that my success is 0.51. And notice how this one said greater than or equal to 3, right? I can't find less than or equal to or greater than or equal to. I can only find less than or equal to. So what I'm going to do is I'm going to find out the failures. There are 2 of them. But I don't want the failures. This gives me 2, 0, or 1 situation, right? I want the successes. So I go 1 minus that. And what you'll see is that'll give you the same number. So you have a choice now. You could either, in the orange, calculate each individual one separately if you want to, or you can do the accumulation of all the failures in this particular case, because it said greater than or equal to 3, which means 2, 0, and 1 are the failures, and go 1 minus that for the total probability and find it the same way. Your choice. The thing that we just got done with in the binomial CDF is what is talked about right here. So the number of trials, the probability of success, and how many successes you want is less than or equal to. With the CDF, the problem is that we actually found the failures and then we did 1 minus to calculate the success. Down below is a calculator tip. You cannot write down what your calculator is saying, this binomial CDF or PDF or whatever that they're talking about to get credit. You have to at very least indicate what the values represent. So you could, if you wanted to, if you want to write down the binomial PDF, you could say binomial PDF 5.25.3 and say the 5n equals 5, the p is p equals that, and k equals 3, and get credit. So you could do that. It's right down here. I'll show you. If you write this, if you write down the green and the yellow together, you can get credit on the AP exam. Because you've explained what each of these numbers are representing. You've defined them. If you only write the green, you will not get credit on the AP exam. So you can choose how we did it up above, or you can choose the green and the yellow highlight in order to get credit on the AP exam. On this next slide, they're talking about some definitions. So we have, in everything we've been doing with statistics, we talk about we want something that's an approximately normal distribution so we can calculate some things. And when you do that, you're always talking about means and standard deviations. When you're talking about a binomial distribution, they define 2 things. They define the mean in this to be the n, the number of trials, times p, the probability, in this case of success. And then the standard deviation is very similar. They talk about the standard deviation being the square root of the n times the p times the 1 minus p. Now that looks really confusing, but really it's almost exactly like the mean, except you do the success and the failure together. So if I talked about, again, my basketball player, and I knew I was shooting 10 baskets, the second one in the yellow highlight would look like this. The square root of 10 times 0.75 times 0.25. Okay, that's what it would be talking about. And I'll show you an example, but that's what it's doing. Whereas the first one would be 10 times the 0.75 for the mean. On average, how many baskets would I expect to make? Well, there are 10 things, and I did 75% accuracy, so I made 7.5 baskets on average. And this only works for the binomial, success failure. Since sampling without replacement leads to violation of independence, now that means if I have a deck of cards and I say, okay, Sam, pull a card out, what's the probability of getting a jack? You know it's a 1 in 13 chance if you don't have the jokers in there in a normal playing deck. And I don't put the card back. It's not a 1 in 13 chance anymore. That's the without replacement that they're referring to. Okay, so when you have a big sample size, simple random sample of size n, we can use the binomial distribution to model the count of successes. As long as the sample is 10 times what you're talking about, 10 times. So this says n is less than or equal to 1/10 of n, the population. But they're saying that the population, another way to say this, a better way I like, is this. This seems kind of confusing. This means that your population is 10 times the sample size. So for example, if I was talking about people shooting free throws, and I talk about 10 shots, for example, maybe that person shot 1,000 shots at the free throw line that season, and when I take the sample, then what I'm saying is the 1,000 shots are at least 10 times the 10 shots that he was taking as my sample. Okay, so you want your population to be at least 10 times the sample size.
It can be more.
It can be more. It has to be at least, I should say, greater than or equal to 10 times. Good question. All right. And then down below it pretty much says the same kind of thing, NP, 1 minus P. This stuff down below is saying both N times P, which is your mu, or in other words your mean, should be bigger than or equal to 10, and also your failure, when multiplied by the number of trials, should be greater than or equal to 10. So there's actually three main things that you're looking for. One is your population is at least 10 times your sample. The second one is when you multiply your trials times the success probability, that should be bigger than or equal to 10. And when you multiply your trials times the number of failures, that should be bigger than or equal to 10. You will do this check every single time you do one of these binomial problems. Every time you will state those three things. Every time. Let's look at an example, which will help see what's going on. So we have this survey. 506 teenagers from 14 to 18 were asked a variety of questions about finance. One of the questions was if they have a debit card. Suppose that exactly 10% have these cards, and X is the number of teens in a random sample out of this 506 who have this debit card. Let's talk about it being binomial. So that binomial thing were the four conditions to start out with. Number one, the first thing is it binary? Yeah. Either yes, they have a card, or no, they don't. Second question was, are they independent? Kind of iffy to me. I'm going to say maybe. The fact that when you take a kid out in the sample, and now you say the likelihood of the next kid being asked, the probabilities aren't the same, because you're not replacing that kid back into the pool, where you could pick that same kid over again. So this is the replacement thing. So maybe it's not, I don't know. That's kind of confusing to me, I guess. But I would say that since the sample of more than 500 is large, probably. So when you're taking this huge sample, the likelihood that that influence of that one person is such a small thing is probably not going to affect your probability of success. You know what I mean? Remember that when you're talking about independence, what we're saying is if I pick John as my success because he has a debit card, and I don't put him back because I don't want to pick him again, then the next person I pick, like Laura, has a smaller probability. Instead of being 1 out of 506, it's 1 out of 505. The probability is different. But since the sample size of 506 is so huge, the likelihood that that probability is going to greatly affect my outcome as far as what I get as my end result is not very likely. So kind of independent, but not really, if you understand what I'm saying. The probabilities are a little bit different, very, very small difference. But there is a difference, because there's not replacement. Mara, this particular part. So the next part is we're supposed to say something about the number. Did they define a number? Yeah, they did. They told us that the number was equal to 506, right? And then the last thing was, did they define the successes? Yeah. And the answer is yes, they said it was equal to 0.10, or 10% of the sample would have successes. Or they defined what they wanted. So now we're going to check the conditions. This is the thing I was talking about on the previous slide about the NP and the sample size and all that kind of stuff. So first thing is, when we're checking these, N times P, is this greater than or equal to 10? How do we check? We go, oh, okay, that was 506 was the number. The probability was 0.10 for my success. This is equal to 50.6. So, yep, that worked. That was good. What about the other condition of N times 1 minus P? Or in other words, is this greater than or equal to 10? And so I have my 506 times 0.9. And that was equal to whatever the remainder is. Thank you, 450.4. So, yep, this is good. And is the sample, or sorry, is the population, the population is at least 10 times the sample, because we're talking about teens, right? There's probably going to be more than 506 teens. So the answer then is yes. We can assume it's a normal distribution, approximately normal distribution. How about the mean and the standard deviation? So the mean and the standard deviation, if I'm calculating these down below here, I look at my mean is NP. So I think we already did that, right? We did 506 times 0.1, which is 50.6. And my standard deviation was the square root of N times P times 1 minus P. Or in other words, the square root of 506 times 0.1 times 0.9. And my sources say 6.75. Okay, so now we're actually going to calculate a probability, or the likelihood of something happening. So we want the probability that 40 or fewer teens have debit cards. So when I do this, I'm looking for the probability that my x is less than or equal to 40. Now in order to do this, remember we talked about the approximately normal situation. So whenever we're talking about that, we can standardize things. So we should probably find a z-score. So we find this z-score by taking our score that we're talking about, which was the 40. Does this color suck or what?
Yeah.
Okay, sorry. So my z-score is equal to 40 minus whatever my mean was, which was 50.6, divided by my standard deviation, which was 6.75, for a z-score of negative 1.57.
Yeah.
Good enough. 1.57. So now this is telling me that when I'm finding my probability, it's really the same thing as saying the probability that my z is going to be less than or equal to negative 1.57. So I can just write that down, whatever the answer is. I think that you find out when you do this on your calculator, you get 0.0.
CDF.
Yeah.
582? No.
Yeah.
582?
Yep. Okay, so the great news about geometric is it's extremely similar